Today, we will demonstrate 5G integrated sensing and communication for spatial intelligence, with 3 positioning and sensing use cases enabled by the BubbleRAN architecture. Our first use case is real-time UE positioning. In this use case, we provide a smooth UE tracking experience even in complex indoor environments. The second use case is human and object detection. By monitoring the power between RU and UE in real time, we can detect human movement and presence. Finally, the last use case shows the multi-UE spatial density estimation. By getting spatial data from multiple devices, our system can identify hot spots of activity or collision risk zones. Before going through each use case, let me first introduce our over-the-air indoor testbed setup. Here, we use a Lighton 7.2 radio unit and a Google Pixel as the UE. The near real-time RIC and X app are running on top to collect real-time SRS signal data. At the same time, we run 2 applications on the side, one for real-time SRS signal visualization and another for real-time UE positioning results. We also placed 4 antennas, as shown in the figure, pointing in different directions to maximize spatial diversity and improve positioning accuracy. Let's start with the first use case, real-time UE positioning. The system continuously captures uplink SRS signals from the UE and converts them into spatial coordinates in real time. Here, the green dot shows the estimated UE position, while the light green trail shows its movement over the past 3 seconds. The glowing region around the dot represents the model's confidence distribution. Red means a higher probability of the UE's actual location, and blue means a lower probability. The floor plan corresponds to our real indoor test environment, including walls and obstacles. The red track shows the actual walking path during testing. Let's take a look at the video demo. In the upper right corner, you can see a live video stream from the lab, which shows the actual physical location of the UE during the test. We first start the SRS plotting application. The upper plot shows the received power from each antenna, as well as the average power. The lower plot shows the waterfall visualization of the raw SRS data, including both amplitude and phase. This figure shows the physical setup of the test environment, including the RU and antenna positions. Next, we start the UE positioning application. Here, I am standing at the upper left corner of the U-shaped path, near antenna 4. On the dashboard, antenna 4 has the strongest received power, and the estimated tracking point moves close to my position. As I start walking forward along the U-shaped path, the tracking point follows my movement in real time. You can also see that the aura around the prediction point changes as I move, indicating the probability range of the estimated UE position. At the same time, the SRS plotting dashboard shows that the received power from each antenna changes dynamically based on my movement. When I reach the upper right corner of the U-shaped path, antenna 2 becomes the strongest, and the tracking point moves to that area. Now I walk the same path again from the upper right corner. As shown in the demo, the tracking point continues to follow the path I walk. Next, let's look at the second use case, human and object detection. Here, we use real-time SRS signals to detect physical changes in the environment, such as a person or object moving between the RU and the UE. On the left, the live power chart shows the received signal strength from 4 antennas. The blue box highlights a significant power drop. This drop happens when someone or something blocks the line of sight path between the RU and the UE, causing the signal to attenuate immediately. We also added an obstacle indicator on top of the heat map from the first use case. When the system detects that the power from a specific antenna has dropped compared to the previous few seconds, it marks the possible obstacle area in red. For deeper analysis, we use the live amplitude and phase waterfall plots. These plots visualize the SRS signal over time and frequency. When a person walks through the path, we can clearly see disturbances in both amplitude and phase. Let's look at the demo video for use case 2. Here, we place the UE close to antenna 3, so antenna 3 has the strongest received power on the left side dashboard. When I block the line of sight path between the RU and the UE, we can immediately see a significant power drop and signal attenuation on the dashboard. The warning message also appears at the top. At the same time, a red oval region appears on the heat map, showing the estimated obstruction area. Then, we move the UE closer to antenna 1. As the UE changes position, the dashboard continues to show attenuation and the warning message. The red region on the heat map also shifts toward the new direction. As we place the UE close to antenna 1, so antenna 1 has the strongest received power. Finally, when I block the line of sight path again at this new location, the dashboard once again detects the obstruction, showing both the warning message and the power drop. Now, let's move to the third use case, multi-UE spatial density estimation. On the left side, the green dots indicate the estimated UE locations, each labeled with its corresponding RAN UE ID. Similar to the first use case, each UE has an aura around its estimated position. This aura represents the probability range of its location. A wider cloud means a wider uncertainty range. On the right side, we visualize the spatial density across the environment. The color coding is different from the first use case. As shown in the color bar at the bottom, yellow indicates the likely area around a single UE. Red represents higher UE density, where the likelihood regions from multiple UEs overlap. Blue indicates low likelihood, or low UE density. The key indicator here is the deep red area. When multiple probability clouds overlap, the system marks that region in deep red as a collision alert, indicating a high collision risk. Let's look at the demo video for use case 3. On the right side, the live lab video shows our 2 UE setup. UE1 is the moving target, while UE2 is placed statically near the bottom left side of the RU. Now, UE1 starts moving. As UE1 moves closer to UE2, the overlapping region on the heat map turns deep red. This is our collision alert, indicating a high collision risk. On the left side, we monitor the received energy of both UEs separately. Since UE1 is handheld and moving, its signal trace is more dynamic and less stable than the static UE2. Now, we move UE1 again, following the same path. As shown on the heat map, the collision alert appears again when UE1 approaches UE2. At the same time, when I pass between the RU and UE2, the received power of UE2 drops significantly because the line of sight path is blocked. Finally, we repeat the same path with UE1 passing by UE2 again. When the 2 UEs get closer, the deep red collision alert zone appears again. In this use case, deep red is reserved for collision risk, while yellow shows likely UE areas and blue or green shows low likelihood areas. To summarize, this demo shows 3 key achievements. First, we built an ORAN-compliant sensing architecture using the LLC service model, enabling real-time data collection through the near real-time RIC and XAP. Second, we process raw SRS signals in real time. By combining multi-antenna amplitude and phase analysis with machine learning-based localization, we can track UE positions in the indoor environment. Finally, we demonstrate passive spatial sensing using existing 5G infrastructure. The system can detect human and object movement, and also monitor multi-UE positioning and density for collision risk awareness, without adding extra hardware. This demo shows several potential applications for our 5G indoor positioning and sensing system. First, it can support virtual geofencing and proximity-based collision prevention in safety-critical environments. Second, it can enable real-time tracking of drones, end devices, workers, or automated guided vehicles in smart factories and autonomous navigation scenarios. Finally, channel analytics can help us better understand the physical environment and optimize network resources for improved performance. That concludes our demo. Thank you for listening. Following the main demo, we have also prepared a few backup slides to provide more technical details on the real-time visualization pipeline and the positioning model workflow. This slide shows the workflow of the real-time antenna power plotting application. On the data side, our XApp extracts raw SRS signals frame by frame into structured text files. The plotting system then pulls the latest complete for antenna data to compute the average channel power, transforming the raw I and Q samples into a decibel scale. By generating live power line plots alongside amplitude and phase waterfalls, the system allows us to detect physical changes, human movements, or object blockages in the environment in real time. This slide explains the workflow behind the UE indoor positioning application. The first step is data collection. We collect the UE's SRS data at known physical positions. Our toolkit automates this process to enable high-volume sampling while transforming the raw 5G signals into an optimized 32-dimensional spatial feature vector. Next, we use this dataset to train a random forest regressor offline, allowing the model to learn the mapping between the extracted spatial features and the UE's 2D position. Finally, we deploy the trained model for real-time inference. The exported .pkl model is used to continuously estimate the UE's position and visualize its spatial probability distribution in the positioning UI. The table here summarizes the data features we use to train the positioning model. We first process the raw SRS data with an IFFT to bring it into the time domain. Then, we analyze the phase differences across antennas and transform the raw signal into a compact 32-dimensional spatial feature vector. The first 16 features are channel impulse response taps, which act like a multipath fingerprint. They capture the dominant line-of-sight path, as well as early reflections from the indoor environment. The next 8 features are phase-related components. They measure the phase differences between our 4 antennas, which helps encode the angle of arrival and gives the model a sense of direction. Then, we include 4 power values in dB. These serve as distance-related indicators by capturing signal attenuation and path loss. Finally, we add 4 statistical and differential features to help the model better understand spatial patterns and symmetry across the antenna array. This slide explains the 3 main reasons why we chose random forest for the positioning model. First, it is robust with limited data. Collecting real-world 5G positioning data is time-consuming, and random forest can perform reliably even with a smaller dataset. It also helps reduce the risk of severe overfitting, which can be a challenge for deep learning models. Second, it is edge-ready for inference. The model is lightweight and can run directly on standard CPUs, which makes it suitable for low-latency, real-time positioning. Finally, it works well with our physics-aware features. Since our feature design already captures the structure of the wireless channel, a tree-based model can efficiently map these physical signal patterns to accurate 2D spatial coordinates. From the demo, we can see that the system is already able to provide real-time UE positioning and tracking. However, when moving toward more complex and dynamic indoor environments, there are still a few challenges we need to address. There are 2 main challenges we observed. First, the position tracking can sometimes become unstable when the device is close to a wall or corner, because the radio signal propagation becomes much more complex in those areas. Second, the use of exponential moving average to maintain tracking stability introduces a latency of about 500 millisecond to 1 seconds. To address these challenges, we have 3 directions for future improvement. First, we can explore deep learning models, such as 1D CNNs, to better capture complex signal patterns caused by wall reflections and improve tracking robustness. Second, we can implement adaptive filtering. Instead of applying the same level of smoothing all the time, the filter can adjust dynamically based on the UE's movement speed, helping reduce delay while keeping the track stable. Finally, we can upgrade the current random forest approach with incremental learning. This would allow the model to continuously update and fine-tune itself with new data in real time, without requiring a full offline retraining process. This final backup slide walks through the end-to-end procedure for bringing up our over-the-air 5G testbed from bare metal. It shows how we deploy a 5G network using the 7.2 split architecture, and connect it to a Pixel phone as the UE. In parallel, the near real-time RIC and X app are running, so the X app can receive SRS signal data through indication messages with a delay of around 5 to 6 milliseconds.